finish the exam, the question, and then using tables, and that will be enough for tutorials. You now also do a lot of them on your own. Finish that part. If I can just quickly put it here. What was the direction of the arrow? I eventually got the nomenclature. Sources. So this is the current source. If the current source is in this direction, then we will write it properly. Current flows from positive to negative. So if this is the plus, this is the current source and this is plus minus, then the voltage source is, I think, minus plus. This is the current source. If you draw it with plus minus, you want to put it without plus in the voltage source. Now, we draw the arrow. This arrow by what convention? I'm forgetting the kind of word used. The arrow is to show you the high potential is where the arrow is coming from. So if you look at the manuals, and you are looking for the V in and V out. So if you are having our transistor, for example, and you have the ground in here, you have VBE, we draw the arrow from high potential to the ground or to the low potential. So that's why when we are doing the other one, the current we were supposed to be doing down. For the current source, it's okay. After drawing it, you have to put the arrow of where the current is flowing. But for the voltage source, the arrow shows you that here is the high potential and this is the low potential. So this is plus, this is minus, meaning that the current from the voltage source is opposite to the arrow. I thought I could clarify that. I have to do it for you. So here the current will be flowing this way, and here then we will be having the potential being high here, and here the current will be flowing this direction. I can confirm about some people draw them this way, both of them, but then use the plus and minus to clarify. So to clarify on the issue, on the case where when we're using superposition, when we had to get the 6 and we were now confused how we end up with 2 milliamperes, the current flowing from the voltage source is from the positive terminal. And when we are drawing the arrow is from high potential to low potential. You close your laptops and write notes. Because there is no evidence that when you open your laptops, you are doing better. And I'm going to be chopping the example, the question which got nothing to do with web. The Swedish are spending now a lot of money to go back to the paper stuff. But I can give you a trick of why you should be careful with electronics and digital stuff. When you have my notes on Mwele, you keep thinking that you got them. So when I'm teaching, you even just, if your mind thinks about some things, you can use it to think about them. Because you got the notes. Now, when it comes to exams, everything looks strange. Because you don't even remember. But if you just get your note, your pen, your notebook, and make sure, in my primary, second grade, and I think a little bit of university, it was as if I was an investigator. I always had a side book where I note what the teacher says that is not part of the note. If he makes a joke, then I write. That's why I have a camera now. My side talk and jokes are always on record. So if I am like, did I say this? Or did I say it this way? I just go back to my camera. Okay, so we want to look for the idea is that we want to look for the current flowing across these 2 points A, B. And now, if we move to Thevenin's equivalent, that means that we have all this complex stuff. These current source, voltage source, the resistances, we got them as our network. And then we say that in a network where we have a 2-terminal output, which we are thinking now as, this is now our new 2-terminal output, A, B. We shall represent the whole stuff as 1, Thevenin's voltage in series with the total resistance of the system, which we shall also call Thevenin's resistance. This is Thevenin's voltage. And if we are looking at the current flowing there, that means we can do this. And then we have our 2 terminals. And now we shall isolate this resistor as our load that is feeding on our voltage, on our source. So this will be our AB, and here we shall have our resistance, our load resistance, which is now 0.1 kilo ohms. And now the current that will be flowing will be I4. So we got, the task we got is to find the Thevenin's voltage. That's 1. 2, to find Thevenin's resistance. And then we just use this and have we got one loop, one closed loop, and then we use the closed loop rule, Kirchhoff's law, and then we shall be good to go. So I want to put that here since I have explained it. So I got the voltage source, Thevenin's resistance, 2 points A, B, the resistance that we have. We are going to keep this resistance in the basket somewhere until when we shall need it. Here, that's 0.1 kilo ohms. This is A, and our current will be I4, and this one will be RTH, this will be VTH. The loop will be giving us an equation that the produced EMF, sorry, this source, VTH, will be equal to I4 RTH plus 0.1, or why just call it RL for now, plus I4 RL. So therefore, I4 will be VTH over RTH plus, where RL is equal to 0.1 kilo ohms. Once you got that in mind, the rest is a piece of cake. So we have opened up the circuit. We have the current source, we got the 0.8, we have opened that, we have the R2, we open this place, and then we have R3, then with source. Yeah, we don't remove nothing, we keep everything. And you see that result. Okay. So this is R3, 2 kilo ohms, R2, 3 kilo ohms, R1, 0.8. I write all these things not because I have free chalk, but the more you practice, the more things stick here. Just like how most of you, the ladies, when you are girls, I don't know that you still do those things. In my LO level, girls had books for lyrics, all those love songs. They would write nicely the lines, and when we are in free time for them, they are there singing. You see them putting emotions. Now, when the numbers come, then they say, we are girls. We're not supposed to do hard things. These days, I don't know. But these songs these days have lyrics.
Yes.
These in Naoro, they have lyrics. So here we got the, we want to know the voltage across here. It will be VT. After we have gotten that, then we shall remove all sources and find the resistance at the same spot. So we shall have no, so we said when we are removing the current source, we just disconnect. So we shall have 0.8 ohms. Then we shall have 3 ohms. Then we shall have 2 ohms. And at the same spot, we shall find the RTH. After we have short circuited this and open, we call it open circuiting. This is open circuiting, then short circuiting. That's what we are doing, if I remember well. R2, R3. The rest, I normally call it algebraic gymnastics. So we want to know the PD across here. This current, some of it will go, some of it will go here, some of it will come here. So we don't care what goes there. We only care what will be going around here. So we have this and this giving us a potential here, and then we have this giving us a potential here. Doesn't matter. Whichever value we get, finally we can take the difference. But of course, you have to be careful. This one will be having if this potential seemingly, it will end up being up there. So it is in this direction. And we say the current here is in this direction. So where would it be going? Also going there. So how do we get the torque? Torque. The sum. No problem. So the potential A and then potential A. So potential at A we have 21 milliamps. So that's 21 times 10 times 8.8 times 10 to the power 3, and then we end up with volts. Those will calculate. Here, ground. Oh, you are doing it very fast. John. 16.8. 16.8. I'm not a good Benon. I don't know how to use my Benon. How is it called? That thing. Potential at B, VB will equal to, this is where the fun is. When you look at the, here, we have a voltage here, we have a resistor here, but seemingly it ends up being the potential across this other resistor. That's when we join these two parts. Here we got the potential VA, and then here we want the potential across here. I can't draw it there because my board is done. Actually, what we are seeing is this point here, and if I can elongate, I can push this resistor here and push it, put it there. And then the source will be around here. So I have this 2 kilo ohms here. I have the source here. And then I have the 3 kilo ohms here. And then I have my point B here. This is the reason we recover the potential divider. So in the other case of the superposition principle, you would have to use the current divider. Here we use the potential divider. So that means the 21 volts here is now the one which will be divided into these two to get the potential across. So it has to be how you visualize stuff. You asked for the potential, you got the potential. So if we have a current, then you'll be thinking of resistance times the current. But you have the potential, meaning that if you are now looking at a potential somewhere, this one is being divided by these resistances. So you quickly have to figure out how is this potential divider shaped. So we need, it doesn't matter, you got two resistances here, you need the one through here, this is the potential divider, you take the one in whose position you need the potential. So this would be 3 over 3 plus 2, and then multiplied by 21 volts. Satisfied. If this potential is, this current is this way, so if the current source is having a current going this way, the potential will be in the opposite direction. So if it is current is eventually going up, the potential will be down. So but this is the biggest. Let's go there. So the current from the 21 is flowing this way, but I don't want you to suffer. Just get the big minus. So the current will, if this line is joined, this current will, the portion of the current that will cross here will be going this way. And the current that will be crossing here will be going this way. So if we take this to be positive, we shall, this one is, okay, they are opposing each other. And we shall take the magnitude of this, Does that help? But if you do a bunch of numbers, then you start getting a feeling of how you can easily find out which one is it. One is small, the other is big. It wouldn't have had the two. It has to be the... So, BTH, yes.
My confusion usually comes at that point. That 16 is the potential drop across 0.8 volts. But it doesn't tell me what's A, it
points are the same. Okay, they are the same potential, logically. And so we are looking at, that's why we are looking at the potential across here in relation to A, and the one which will be across here, which we have successfully found out. The question now is, which one is going where? The other side, they are all at the same point, up there.
But I suppose there at B would be the same as 21.
It's not the same as 21.
Then after R is where?
It's not the same as 21 at B. That's why, because this point is the same, so this 21 is also connected to this point through this resistance. So this potential here, okay, this voltage source is being affected by the drop in this resistance. So it can never be the same as 21 because it drops. The reason when we are having a voltage source, the reason we have to be concerned about the nano resistance, the RS, we can call it the nano resistance, is that it always drains our source to the extent that your dry cell will reach a point when the nano resistance is too much that it can no longer work, can no longer allow the current to go through. But the challenge we are having is visualizing where the current is flowing and where the potential will be flowing, the resultant potential. But we have said that from here, if the arrow is up, the current is going down, and that means the current provided by this voltage source is flowing this way. Part of it will go up, and then we have this one current. If the current source is going, the current is going this way, the potential will be going this way. And but I need one to hustle. The potential across here, we shall get this big one minus the small one. I will take the difference and take the magnitude because we want the potential across. We don't care. We are connecting on a positive and a negative terminal. We never say, are we looking at it as in terms of the positive or the negative? We just want to get the potential. That's why we are interested in the potential difference. So our VTH will equal to VA minus VB, implying that VTH is equal to, or we can say therefore VTH is equal to 4.2 volts. We got it here. Now we need this because we already got our load. So we come here. Start from the foot soldiers. Remember? We start from the foot soldiers. This is where the commander is. So don't start from here and there. Okay, these two look in parallel. Start from the foot soldiers, far away. So RTH will be equal to R1 parallel to R2 parallel series. We say this is series. My mind is very crooked. And then parallel R3. So this would imply that RTH is equal to 0.0 kilo ohms parallel OIR. Okay, thank you, since you are saying very right. So add on, where are you rushing? Over 5. So this is k squared, this is k, 1k will go. So k ohms. Therefore, RTH equals to 2 kilo ohms. I don't remember how many marks I was giving in these things. But I know it was 5 marks for superposition, 5 marks for this. So, and for superposition, the two circuits I was giving 1 mark, 1 mark. For this one, it was half. Half here, half here, half there. Probably half here, half here, half here, half there, half here. Then the rest I will give as I wish. If you have done this nicely, I put. If you just give me an answer, I ignore. There are some of you who quickly think that steps are not necessary. I don't know how you got it. So RTH equals to 2 kilo ohms. So I got everything now. And then I can find the I4. So I4 is here. From I4 is equal to VTH over RTH plus RL. This would be the same as 4.2 over 2 plus 0.1. These volts, these are all kilo. These are volts. So this would be 2.1. So therefore, I4 is equal to this is 1,000 delta becomes times 10 to the power negative. Now somebody did this, it was 2. But for superposition they were having 10. 14. Or 14. Are you the one who got 14? So I was wondering, how do you get 2 here? And you can't say, but then you go back and check out. But how do you get 14 amperes?
It's easy. You have 6, 7, 8.
What?
You have 6, 7, 8 is 14.
It's okay, you can make that mistake. But if you make that mistake, if you came back here, this current there, and this current here, this one divided by kilos everywhere, you can't get anything above an ampere. The other one is already nearly. If you get anything above an ampere, you should. I want you to have a questioning mind, not cramming machines. Don't be cramming machines. So that's not what I want you to do. I want you to be inquisitive. Say, why am I getting this in the first place? That's how I used to. That's why. I was not a genius, I can't say, but I would do what I know. I would go in the exam, write what I remember that I read. When I finish, I finish. I close my paper, I hand in. I go to look after notes, if it is in the evening. If it is lunch, I go to change them, where I have left them tied. But these things of you are writing, you are looking for who is asking for more paper. There are these fools who would say, they get a paper. When results come, I don't know what they were up to. Even in the final exam, they were like that. They were asking for a booklet. So for me, when I would get exam, it's my business. I chop. If I'm tired, I go there. Even when you look at my marks of A level, you like this for practicals, I don't know. So in the morning I would be okay. Afternoon paper, I'm tired. I go. Any question about this? There is no excuse. I told, I explained. I gave it in the test, I'll explain. If you go there and you cannot solve the determinants thing, that is your problem. Yes.
How about solving the same problem using autonomies?
See, there is a statement here, so I'll read it for you in the book. Don't worry, I'll read for you the statement in the book, which will help you. But this is your Norton. That part here, this part here is a Norton equivalent circuit, which is convertible into Thevenin's equivalent. So, but I want to read something for you. If my eyes allow, page 23. I normally never want to be called proud, but I think I have to get the glasses. Okay, I'm reading for you what you asked me. A second form of equivalent circuit useful in situations as, for example, transistor circuits where current sources rather than EMFs have major interest, is one given by Norton's theorem, which states that any network of barriers and resistances having two output terminals can be replaced by a parallel combination of the current source and resistance RS. The current source RS is the short circuit current in the output terminals, while the resistance RS is the same as that of the Thevenins. Okay, so since it is possible to represent any network by either the Thevenins or Norton's equivalent, it must be possible to convert from the equivalent circuit to the other. Right? And thus, it is simple. It is a simple matter to convert from the circuit, from one circuit to another. Which circuit is used to represent any given network, and is another matter of choice and convenience. So I don't know what you want me to do. I've been reading the prophet. Any other the technical bit of this, not the.
But if I'm sorry, that you first get the other 7 resistance.
You first get the RTA. Was there anything we used from VTH when we were looking for RTH? The issue is that I drew this diagram and said, as long as you've done these two, you have already kept this RL for your keeps to use as well, so you are done. Whether you started by getting this or by that, it's your business.
Okay, like before so far.
Which if? 1, 2, or 3? the issue is if this question was clear, use superposition principle and determinants. But if they just ask you to find I4,
Can use calculus.
you can use a calculator if it can give you anything. The other thing I want you to do is that you change this one in a voltage source and see whether you can take these ones as loops, and then and also the case here, one for the currents, and see whether you can use Kirchhoff's to find the I4, so that you can use Kirchhoff's, Thevenin, superposition, and Norton. But Norton is more or less like, again now converting a current source into a voltage source, and then you still use the same method. It's like interchanging. It's no big deal. Depends on how you want to look at it. I am spending more time on this because to me these are free marks. These were free marks. 10 marks on one number out of 30. Okay, so let's get back to business of the experiment. Experiment 7. Is it 7 or 3? Come on and make an amplifier. I made a promise to myself to simplify stuff. May God help me to always try to simplify stuff. So that, but I don't think now there is anything complicated that I will need in physics that then makes me complicate. Is there anything now beyond this level? So experiment E3 is the common emitter amplifier. Maybe before I move on is so E1, E2, so by the end of today, E3 will be done. So first we are now an amplifier, meaning that we finished the BJTs, and then I put assignment 1, the offline one. The online one now is still compiling the questions, because online assignment 1 is 100 numbers, online assignment 2 is 500 numbers. Objectives. So the offline one, which you have to type and hand in, you have to hand in groups as you are in groups of practicals. You hand in 1 copy. You can only upload 2 megabytes. You can't go beyond that. So I don't remember the assignment in my head, but you need to write short notes. So it started today, after telling you now. The deadline is on April 3, April 3rd. At 17 hours. There is an upload link. When you go there, you click on it, don't worry. It's not like the online assignment where you click and then when you say attempt, then it gives you 0. This one is okay. You'll be able to upload your work. And I think, I don't know the structure, uses, operation principle and operation of field effect transistor, so that you also do some effects. This is experiment 3 in the lab. We have a circuit. Then we have the transistor. Everyone now knows how a transistor looks like. Knows how a diode looks like. No, at least for a diode, maybe all of you. A diode, the transistor, a LED, so we said in an amplifier we have the input voltage, we have the output voltage, and the amplification would be the ratio of the output to the input. And using this potential divider, we can bias the transistor. So this is the RC. How many have done E3? Those who normally don't, what are they doing? So all is over 10 students are not around because you did a test when you are 54. Even the one fellow who missed the test, it's like he takes it normal. But when you miss a test, I didn't see like an urgency of like coming to me and say I missed a test. I sent for him and he came to me and he was like, you said that you want me. And so I was busy with some guy. I said, yes, you see by the time I sent for him means you are not around. He said, okay. I said, you can go now, I'm seeing you, let me finish with this gentleman and wait. He went. Doesn't do practicals, he doesn't want to do a test. Mubiru, are you interested in doing this course or you are a tourist? Eh? You want to, it is part of what you register for. When I laugh like that, you know what it means. So, what if I say I'm taking test one only? What happens? Like if I become malicious and I'm like, test one, you did fairly well, it's okay. That's all we are going to do. I don't know how to explain to you, but I don't know how I can say it nicely, but for me, when I reached Makerere, I say, you know how these people who are tired, how they say, like, you breathe out deeply, and you are like, I have arrived. So I said, I will not go back to the village. That's what I said when I reached here. My first day when I went to the main building, that was my first time of seeing the terrazzo, like that floor. It's like they designed it. It was like, I have not entered there since when they renovated it. I have not entered the main building. But that day when I came to pick my admission letter, when I entered the main building, it was like, I've never seen such a floor. I could have seen it before, but you know, I don't know, maybe even at the school I was probably one of the buildings high, but it was amazing. I said, I'm not going nowhere. Then I came here, this building, this big size wall. I'm like, I'll work hard. I don't know for you, are you born from around like Kasumi or what? It is typical of the guys who are born around to find that they used to visit here, like come and visit their friends here, so it's not a big deal. For us who came from the village, we said God has brought us, we are not going nowhere. Tofa, you are reminding your friend that he should also think that way. So we covered the small signal equivalent circuit. Really, yes, this is fair. So any DC voltage sources, any direct current voltage sources. I am this, not lousy, I'm this sketchy because those of you who have already done E3 or who will do, you will experience it in the lab. And maybe the other thing I want to warn you about, not warn you, but urge you, don't come in the lab when you are green of the practical you are going to do, green of the, are you registering for the first time or for some friends whom I have complained that they are not around? I know all the people who are around. If I look through and I see some name, I can know who they are by using the, do you get my point? When you go to the lab, this experiment here will give you a chance to find the characteristics of the input and output. Experiment E1, you draw the graphs you are seeing, which is the full wave and half wave. Experiment 2, you draw the Zener diode characteristics. you should be having this theory. So when you reach there, you try to see whether you have gotten the thing. But don't get, you are supposed to be getting a graph of this nature for a Zener diode. You get points, and then you find that there is a stray point there, then you do it. Because you want to follow that point. I'm not saying that you forge it, but when you know what you are looking for. Yes, draw what, give the data you have got, but then also be able to give, remember when we were doing the guidelines, be able to give a corresponding conclusion. If you are failing to get any points that would make you have it here and it ended up there, explain why you are having that anomaly. But with this idea of what you are doing, when you are trying to adjust, you'll be having a sense, like some group was doing the output characteristics, I think it is the poles, and they were like, but sir, it is not changing, it is not changing. Now, where was it supposed to change to? If you are having the values here, along here, you want them to change where? I'm sorry to have named you directly, but I'm trying to give an example that go to the lab. I know it is a challenge that we are not going to the lab to do the practice of what we have already studied in theory. But we got everything. We got the internet. We got the phones. Some of you have a boy who know all the names of the Bundesliga players. But when it comes to academic things, he looks up when you ask something. But he knows even how to pronounce them. You know that it is not Bayern Munich, but Bayern Munich. He knows the names, he can pronounce them nicely. If you can take time to really understand these players, even when they are in a match, even small one, he says that one is so and so. And these are people who are just making money. They are in the pitch making money. You are there appreciating them. You got nothing. These people, but to comfort you, these people never enjoy their money. They are always in pajamas called jersey. Ronaldo makes millions of dollars every week, pounds, whichever it is. But he's always in pajama. He can afford nice suits, he can afford nice shoes, sleek shoe, but he's always in a shoe which he can't even walk comfortably. How many of you play football, eh? Those, how do they call those things down? I've never put on a football shoe, I don't know how it feels. They call what? Spikes. When you are walking on them, you don't feel at home. It is uncomfortable. He has no time to enjoy his money. You got nothing. The library is more comfortable, but you can't even be in a library. But for them, they are always in the pitch practicing. They throw a ball, he kicks, he runs the other side, runs the other side. And then on a Sunday you are there quarreling with friends. He should have scored. So any of these imported sources become short circuits. This equivalent. And so when they become short circuits, we change this circuit in with this form. We have the I don't know, please make sure these transistors of yours are well drawn and put the arrow. I forgot the arrow here. Then we have this RC here. Then we will complete the circuit. Then we have the grounded. Then we have here the and other one, other two also, and then this is the IC. We have, if you look closely, we have now other two short-circuited, other one and other two. So other one is short-circuited, is pulled this way because if we draw this one this way, so we can put this one this other side and it becomes parallel to this one.
So what have you removed? This is
VCC is NDC. VCC is our DC voltage in this case, and we have short circuited it. So we put a wire here.
so you connected it to this.
We put it here on the ground. And when we put it on the ground, so this resistor came like this. And then this part is here, and this part came here. This part came here. So like I do like this wire comes in. And then I just put it here, not to be on top of this. We replace the transistor. Replace the transistor with its small signal equivalent circuit. Remember the circuit for the equivalent circuits. We got the V in, then we got the R1. So we have I1, R1. And R2, here, and then inside the transistor we have the RBE. And then we go to the meter or the ground. So we got a meter here, grounded, and then we go to the other side, which is a combination of the voltage source given by beta IBRE then we have the RC, and this would be RC, and on the output we shall have the load, sort of our load resistance, which is the RC. This RC gives us the potential. So we have R1, R2, I1, dash, IB. This is the small signal equivalent circuit, and we got this from the relationship of the IC in terms of IB and VB, IB as a function of IC and VCE, and VBE as a function of IC and VCE. I don't remember. You can find out. I know some of you are like, now how can you not remember? You expect us to remember. Yes. Before RSC, zero RSC, it's not about this. This is the output within across here, across the transistor. But here we RSC, we short it to the meter, the ground here where there is also the meter. But we have this one as a, remember, it was like this. We have the VCC, then we have the transistor, and then we have the output here, the VR. We have kept this, and this VCC, which is only showing positive, but this power supply also has a ground. Those power supplies in the lab, they have a plus and ground. The ground, their grounding is connected here. So when we short them, when we short the DC, when we short circuit the DC voltage, we have brought this one down here, but we still have this output. That's the reason for this right here. In the lab, I think experiment E3, I'd love to see whether I can show you how the circuit is, so that we get a feel. I've never gotten any number above 45. They're always 45. But we are 55. But no problem, don't worry, I'm not complaining. The exam is on, okay, is it June or May? May. First thing I want to know We couldn't do E6, which is a load line, because it requires E3. And by the nature of how we are doing practicals, it becomes impossible to make you use things of what you haven't done in a one-to-one. Because some of you may end up doing E6, self-pijat, may end up doing E6 before E3. So I was asking the technician why it is not why there is nothing like the E6 when everything is available. And then he reminded me of that. So I just want to know for you the E3. The circuit is like that. Then we have this as 1 meter. I don't know which one it is. My eyes. But should I be crying about my eyes or I should get glasses? That's because you want company. Who said no? I thought it was your phone who said that. It is Sabona. I will. I'm too hesitant to get glasses. People, I'll only get them, maybe put them on when I'm on the radio. But people already think I'm proud, so I don't know when I put on glasses. It will be worse. But should I care about people or people? Yes. I made the resolution much other and put it on paper. Or you say, you do this, you don't do this, we shall not bury you. So I saw people who cremate, and it was cheap. I think it was below under 2 million. That one I can save it. And make sure that in my will, I put that I should not last for more than 24 hours when I die before I'm burnt. And then my ashes should be taken to River Nile at the source so that I can go to Egypt for free. I already told my son in words, but I want to put it in writing. And put the money in how do they how do they call it? These people who go around, we shall say many things on your burial. I will put in my will, no one should say anything about me, whether good or bad. You go tell it to your children or to your friends, but don't say it on my, which is not even going to be there. Because the boy will just carry the ash and go himself alone. And pour until when it is over. And you should make sure he cleans it. Scoop some water and clean it. So there's no. Also, those of you are like, these black people want to say things like my body. You can go and have. So this is the circuit in E3. And those who have done E3, this is what? IC.
First one is IC.
Then down here is VCE. And this one is IB. And this one goes to VCC, which is 15 volts. And then this is the ground. So you have two potentiometers. So when you are just in here, you are trying to vary the current that can go through here, IB. So you can vary IB as you read off the IC and VC in order for you to get the output characteristics. So I think which one is Mugabe? Which one were you supposed to, which experiment were you doing when you were supposed to keep IB constant? Same thing? 15. And then they were always confused, how do we keep it constant? I think even this one, Paul. Even this one, I think you needed to keep IB constant to get the values of the other one. For you to be able to get these ones. So for a certain IB value, you will get these values by adjusting the potential divider. You see, in the circuit it is, I just want you to understand. In the circuit it is like this. Then when you reach the lab, it's a circle with the connection here, a connection here, a connection here. A wire from there, from there, from. So this wire is here, this wire is this one, this wire is this one. When you are adjusting, when you are turning the knob, if it has a knob, there is one with a black knob. But if you are putting the laminate in here to turn, you are actually moving up or down. So that turning is adjusting around the dial. I thought I could make you visualize. And the idea of not much as we have a potential divider here, but you can see now this whole thing is connected to this DC voltage and everything has been taken down. And we still have to look for VCE, Goodman. Yes. We are still looking for this P out here. Even when we put the RC, even when we blew there, we are this way, but we're still looking for the output here, this here. Okay? So when you go for this experiment, go when you have the theory, and you just go to try and have this in practical. I wish I was taught like the way I tried to teach. Maybe I would know more, but it was a different thing. And it could have been better if it wasn't that your priorities are fake. I would now come here, log on the PC here, the projector puts there, and then I start going through the notes on Mwele as I chop a few things which I need to explain on the board. And we will cover a lot. But if we put a PC here, you start with the cable, the mouse. Take away the mouse first. I told the people to bring this wire so that I can put here router at one time, so at this place. Then the students first used this, then we broke off some. Now it looks like as if it is some design, but that was a Ethernet cable. Now V is equal to, according to this circuit, what would be V in equal to as a voltage source? The V is the same as the have you known how what these things are? I don't know. No. I looked. And all our senior guys are gone, and even the senior technician we had also are retired. Maybe my colleagues don't care what it is, but when I would bring the source, the audio source, and see whether it could have been a speaker or something like that.
I tried to look at the label on the
these two inputs here, I feel like maybe they were speakers, because here the design is looking like
Speaker.
it's a speaker. Could have been nice, strong speakers for the audio, whatever in here. The other ones, I think, we are either fun,
Those ones are fun.
they look like fans, and the other thought as if it was for a projector. I don't know.
But in 1952,
Whatever is here. You wonder whether they had projectors. Yeah, they had something like this transparent, but I don't know how it would be there. I don't know what it was.
the transparent side.
I don't know why I'm interested in that. So this would be the same as IBRDA and IC would equal to minus V out over RC, and the output loop equation would be here. The output loop equation would be RC plus RC into IC minus beta IB RC IB RB, not RC. RB is equal to 0. Substituting for IC and IB, then this would be the same as V out over V in. Remember, we are looking at a common emitter amplifier. So this is the amplification. This would be the same as minus RC over RCE plus RC times beta RCE over RB. So the voltage amplification is equal to the output over the V input, which would be the same as minus beta in RC over RCE plus RC over RBE, which is equal to minus beta in. These are product over sum, which is the RC parallel to RBE, RCE, not RBE, divided by this one here, which is RBE. The example we did drain my energy, so that's why I am. Then we need to know something about the input resistance and output resistance of an amplifier. So the input resistance RA is the same as the input voltage over the I1, which would be approximately V explain to you what I wanted to put. So to determine R out, then we got to have we use the following circuit. Use the following circuit, or we use the circuit below. We have the so R out will be the same as E out I2, which is equal to RC parallel to RC. And this one is equivalent to the parallel of R1, R2, and which is far much greater than RB. The parallel of R1 and R2 should be much greater than RB. When you do this experiment, you'll be able to get more stuff than I have listed here. And also, once you read through. So we're going to do this same stuff, this same ritual for the common collector and common base. And I guess in the book, in the manual, E5 is the common base, single stage, and E6 uses E3 to... I gave you a wrong heading, and some of you who saw you didn't bother. E3 is a common emitter, and we've just been doing the common emitter. I'm looking at the different common emitter. So we got common collector for E5. E5 is common base, then load line, and then E7 common emitter single stage, then E8, which is a combination of E4, then we go to the E9 two-stage amplifier, which is beautiful, and then I don't know how this comes up, that shouldn't have come earlier, the wave shaping for the E10. I'm tired, but I have to we're going to do the same. Come and collect bonga. If you continue laughing up there, I'll bring you from next time. Don't be in company with Sempija. Sempija does this course like he has too many alternatives. We used to study with the kids, and it is true because I think one of them whom I used to help designing love cards and success cards for his girls, he now lives in the US. So his mom, I think, was in the US, so he was just studying to finish. You know, these parents who say, just finish, please finish S4. Just finish S4 at least, so that when you come this way, you don't get trouble. So for him, even money spoiled. So for me, I was broke, but not the guy who could design on these girls' success cards. Calligraphy, then I even put their names. Is there a letter here? I don't want to design the word ratio and then someone feels good that I designed their name here. So I would design, you know, make it was seamless. Because with that it was not a problem. I designed it, the whole thing. So when it takes to the girl there, like, you know, it becomes customized. It's like it was printed in the from the computer. There were no computers by then. This Photoshop you do and whatever, smoothen yourselves when the whole face is full of. When you meet the new person, you're like, are you the one? I am the one. Agaba would know, but during our time, they said that if you want to marry your girlfriend, look at her in the morning. When she wakes up, if she pleases you, then you can marry her. This is called a mirror follower. These days you are not allowed to have such privileges, I guess. This is E14. If you try, the payment is too high for the transfers. So E14 is, we're not going to do E14, but in case, I'm not teaching you to just pass exam, but sooner or later you'll be in front of students like I am. If you are lucky, if you excel, you get a job in the university. The other day, one of my former students came to inquire for me. He got a job in Muni. So he came and said, I've been teaching secondary now. I've snatched a job. What should I know? What shouldn't I know? So I told him a few things. So the meter corrector amplifier is experiment E14. In your free time, you can go to the lab and say, what is E14 and you do it. Or you can buy materials. You can't buy anything to understand the course. The transistor is 3,000 or 1,000, I think. One transistor, I think. Does not go beyond 5,000. So a transistor, it's so we have the input here. This week I want us to finish all these things, or I can say say you complete and then we start on the feedback and then hurry to dig it apart. The speed is going to be, now that I've finished the test, I've revised the test, you know what I want, you know what you're supposed to do. So now the speed will be a little bit higher. In the lab, each one of you now knows these components. When I talk of voltage supply, current supply, you don't say what the hell is that, or DC supply. If we are talking about a transistor, you know, diode, you know, breadboard, you know. Some of you have already done D1 for the logic, and fortunately you have done this in mathematics. So we shall now be adding a little bit. So if we have the C1, the capacitor here, C1, and then bias the transistor through R1 and R2, and then we have the transistor, and then what did we say when we, what purpose did we say we put this RE? When we are, this was when we were biasing, when we put RE. What do we do? What are we doing? Fine, but what process was that? This was biasing. This one was what? Stabilizer. So then we say we need this capacitor here, and then we have the grounding, and then we shall get the V out here. Always don't understand. You go even have some small beers. You know this is a lecture theater. Your friends study from there, didn't go around shouting like a fool. You normally study from me. I pass there. Even the shoes I go tiptoeing. Make sure that you study comfortably. You are lucky I will never be a president. You can imagine what could have happened. Because I wouldn't be needing anything from you. I would almost be giving back to you. We note so when we have resistances, what comes to, capacitances, what comes to our mind? What does a capacitor emanate? When we use the capacitor in D1, what was the purpose of the capacitor?
It was smoothing out.
So we eliminate which one? DC or AC? We note one collector is directly connected collector, we got no RC. So the collector is directly connected to the VCC, which is from the power supply. 2. The output is obtained from the mirror terminal. there. But in the multivibrator, the emitters were directly connected to the ground. And they tell you to find those who are doing D14. And they tell you to draw the graphs of at the emitter. But the emitter is connected to the ground. And then when some of you get lines are like, we're not getting nothing. You are getting something which is being grounded. And indeed it is that. It's a grounded signal, so it's a straight line. Third one, we note that the emitter resistor RE has no bypass capacitor. Has no bypass capacitor. Just want to confirm the fact that wrong. When we reached P7, we started putting on khakis. We would turn this part almost going this way. And we thought we were at the top of the world. We went to S1, we became Ngata. We became newcomers. They would pull our ears and say, you go and fetch sunshine in a cup. You go, it fills up. When you enter like this, it goes. When we reached S4, we were now being two again. This flight was fair. When we came to campus, we were all fake. We don't know where. You find somebody asking, where is Lumumba when they are at education? When it is just at work. Life is like that. So these guys are now in the third year, but they don't care. They think that now after finishing, when they reach the field, now they have to rely on the other teachers if they are teaching. I don't know. They know, I've been teaching them for a year. They know there is a lecture here. Some are standing there, they even see the camera and they know it is my lecture, but they still make noise. So I didn't need to talk to them. I just looked at them with my nice eye. So we do small equivalent circuit. The problem, which I thought they know, when you graduate, even if you get a first class, you need a referee when you are chasing for a scholarship. A referee is somebody whom you have had a rapport. You do this in psychology. The propinquity, the nearness. Today they sit together, and tomorrow when they sit again, they start understanding each other because of that nearness, that propinquity. They get a bond. So the rapport is how you react, how you behave with the lecturer. Makes you understand each other, and he knows a few things about you. So when you are chasing for opportunities, when you go to him, he knows what to write. But there are now students who come to me and they're like, sir, I see them, I know them, but I pretend like give a look like I don't know them. Sir, I am so and so, you taught me this, and then I normally burst into laughter. I say, so what do you want? I'm chasing this, I would like you to get me a reference. Sometimes I feel sorry. You spend the whole time here, You didn't come to say hello. In class, you were just always like this. When you finished, you were like, go to hell, I'm done with campus. Then now you are humbling yourself for a reference letter. Or you want to start your postgraduate, you want me to give you a reference, fill your form for masters. Fill what? I don't even know. I don't even remember. I normally take keen interest to know everybody, but there are those who elude me. They just become like invisible. They come here, they just do their thing and go away. So when it comes for your time to look for something from me, I scratch. But there are those who really, I don't know, there are people who are gifted in having rapport with people. You just find it easy. Come meet you and like, how are you, sir? And even talking, then there is that one who meets you and asks a stupid question. Good morning, sir. I say, are you fine? You answer that question. It's like you are forcing me to tell you how I feel. If you have said good morning and I'm saying good morning, then leave me alone. I think you have to find problem. Leave me alone. Let me be. This one. You find somebody insisting, are you okay? One thing I want to warn you about is that when I'm in class here, I'm on a job. So I smile, I make jokes when you meet me in the compound. All the way to my breakfast or lunch, I look like as if I quarreled with somebody. That's my nature. But when I'm here, I'm at work. Jolly, because I have to make money. It's not about that. It's not about making money. I think it is something that I can't blame the training I had. I just mood them. Smile with me today, tomorrow I pass you, and I don't feel anything. Just wanted you to know it, so don't feel like I have an issue with you. Even when you are in the lab, I'm okay, I smile, I laugh. When you meet me somewhere. So can we, this one is which, from that circuit, we are now going, we are making small equivalent, or small, I think we can't say small equivalent, small signal equivalent. Small senior equivalent circuit. So this would be our VIN. Then we have the base. After base, we have the current ID. And then the resistance will be R, VE, then we got the meter, then the meter we have the RE, then we have the collector, then we have the ground. And so then we have something missing here, which will be the output. This is Benon, IV, RC. This is RCA. Oh! just saying, I've just rubbed it. But if you remember, we use to stabilize, we use the capacitor to bypass the emitter resistance. So this is bypass capacitor. I am not complaining because the board is poor at this spot, but I was just saying if you could guess if you have been revising really, and you have been seeing a bypass capacitor, I watch too much TV, okay? Even if I'm sleeping and somebody's voice, whether an MP, a minister or whatever, I'll tell you that is so and so. It could be a gift, but it's because I know each and even if I face this side and a few of you who normally talks, I'll tell you that is once. You can test me, the front row. You just say this is a capacitor. Choose one of you, I'll tell you who the person is. You now want to pretend to be a robot or what? Just to make, you want me to fail, eh? Or we have the V. Then we have the RB, we have the then we have the source here, still rounding, C, that. This is the better IBRC, RI. This will give us the V out. This is the capacitor. IC. This is this is IE. This is IC. This is IB. I'm about finished. If you are, you have maybe 30 seconds. Yeah, 2 minutes. So don't chase me. This is the best. Well, this will be, we shall now work out the amplification, the V out of the VN, then work out the output resistance and input resistance, do the meter follower, and then the common base, which is the last bit of this, and then we start on the feedback. When we do the feedback, then we look at the op-amp, the operational amplifier. Here we are struggling using a transistor to make an amplifier, but then under an op-amp we shall use a chip to provide us everything that we need. And the chip will be, that chip will be having a symbol of this with 2 inputs and an output, then power supplies, for it to do the functions it does. And then we shall draw the diagram of its pins, has 8 pins, then one grounded, the other with the VCC, and then we use the inside. look at the representation of what is inside and look at the add on a few things, make it summing up, the differentiator, the integrator, and then from there we would have now known enough to start on the digital electronics. So let's finish this. Let's use this week to finish all this stuff of the feedback and these amplifiers. Then from next week we start not strictly, but we start seriously on the operation amplifiers. I don't know whether we could have gotten an experiment at least to do some operation amplifier, but I don't know whether we got it. Yeah, I'm trying to push up to the end. So I see you tomorrow at 11. Come when you have some idea, so that I quickly do this, rather than coming here and everything is like you are green. But don't you feel guilty sometimes? See you tomorrow.